These are the notes on Le Chatelier's principle. In these notes, we are going to predict the response of all species or all kind of chemicals in a system to a stress being applied, and then predict the effect that would have on the KEQ value. So what is Le Chatelier's principle? Le Chatelier's principle says that if a closed chemical system, which is at equilibrium, experiences a change or a stress, equilibrium will shift to counteract the change and establish a new equilibrium. So what does counteract mean? That means that if you do something to a system at equilibrium, the system's going to shift in a way to try to undo that equilibrium. So if you add something, it's going to use it up, like heat or a new chemical to that system, and trying to kind of get back to equilibrium. And as a reminder, equilibrium only occurs in a closed system. And so when we have that equilibrium reached, which is what we've been discussing so far this whole unit, now if we are making a change, how can we predict what's going to happen? So examples of counteracting. So kind of again, trying to counteract, use up what was added. If you add heat to a system, the system's going to shift in a way that's going to use up that heat. If you remove heat, well, the system is going to shift to produce heat. Increasing concentration, the goal of the system is going to be to try and reduce the concentration of that substance. And everything else is also going to then have to respond in a way that supports doing this. Decreasing a concentration, of something, then the system is going to want to increase that to get back to equilibrium, and all the other pieces in the system are also going to work towards that goal. If we are dealing with only gases, then we do need to consider pressure. So increasing pressure in a system, well, the system's going to want to try to undo that by trying to reduce pressure, and vice versa. And so here's kind of another way to see that. So the types of changes or stresses we can have. If we look at a reversible reaction, if we have that system at equilibrium, if there is a change or a stress, like the concentration or the amount of something is changed. If we have a reactant that is added, so let's say we are adding A, well, that is going to favor forming products. Because if we have more A, that means that we can use more of B, that's going to go down, and we're going to be able to make more of those products. If we look at kind of that vice versa, if we have more product, well, that means if we have, let's say, more C, that's going to use up D and produce more of our A and B. And that would be the same if we were, let's say, reducing A, that's going to increase B because we don't have as much of it used, but that also then means we can make less of our product. And so it's going to favor actually those, the reactant production. With temperature, if temperature goes up, so let's say we are increasing temperature, so heat in our reaction, and heat can be on either side. So this one we have to think of as where is my heat, and then how is that going to, what is that going to mean? So if my heat goes up, that means my system is going to want to use up that heat. It's going to favor an endothermic reaction, meaning that in that case, it's going to favor the forward reaction, which means that those reactants, those products are going to be favored. If we're looking at temperature going down, looking at where heat is here, if temperature is going to go down, this is going to favor an exothermic reaction. We want heat produced. And so to produce heat, you are going to favor making reactants, favoring that reverse reaction. And as a reminder from when we were talking about heat and energy, endothermic heat is a reactant, exothermic heat is a product. And we have those two reactions going on. So we're looking at which one is going to give us the result that is going to undo that stress. And then for pressure changes, these only impact the chemicals that are gases in our system. If pressure goes up, then the system is going to favor the side with less molecules because in order to get the pressure down, we want less gas molecules in it. If pressure goes down, it's going to favor the side with more molecules to try and increase that pressure and counteract that stress. And we do need to remember that pressure-volume relationship from last unit, the ideal gas law, and that pressure and volume are inverse. So pressure and volume have that inverse relationship with that, and we can see that in the ideal gas law and in our pressure-volume relationship when temperature and amount of gas is staying constant within the system. So how to predict the direction of change with concentration. You should have already kind of thought through this in that Le Châtelier intro activity. And I talked about it a little bit on that last slide, but we can consider what needs to be used or how to undo that stress. And one way we can think of that is same side opposite, opposite side same. So whatever's on the same side of the stress is going to behave the opposite. Whatever's on the opposite side of the reaction of the stress is going to behave the same. And a stress is always going to be indicated for us. One way we can organize this, and just again thinking of what do I have more of, what needs to get used up. I always go through and write a circled arrow under my stress, and then I adjust everything else accordingly. And so an up arrow is going to mean concentration is increasing, a down arrow meaning a concentration would decrease. And then we can adjust and consider how is everything else going to behave. So let's look at some of these. And remember, we are only able to adjust concentrations of gas and aqueous substances. So if the indicated stress is a solid or a liquid, nothing in the system is going to change. If the indicated stress is for a gas or aqueous, it's also only going to change the gas and aqueous substances with that. So if I look at this first one, here's my reaction. My stress is adding hydrogen chloride, HCl. And so if I add hydrogen chloride, and I always just put my stress in a circle just so I know which one's my stress, that's a gas. All of these are gases, so they can all change concentration. So same side opposite, whatever is on the same side is going to behave the opposite. We can treat heat like anything else. So heat is going to go down if that amount of HCl goes up. And what's going to happen, opposite side same. Well, on the opposite side, if I have more HCl, that means that in order to reestablish equilibrium, more chlorine is going to be produced and more hydrogen. So as we look at this, well, what side is going to be favored? The reaction is going to go towards that reverse reaction. We have more up arrows on, and again, I'm looking at my two sides of the reaction. I have more up arrows on my reactant side. Remember, reactants are always on the left, products on the right. And so what side is favored? Well, this is going to favor my reactants because that reverse reaction is going to have to happen in order to reestablish equilibrium. Looking at the next one, adding hydrogen to my system. Hydrogen now is over here. That is my stress in the circle. And again, I like to consider what are the different sides of my reaction to kind of think of how is each side behaving. And when I'm looking at increasing hydrogen, well, same side opposite. If I have more hydrogen, that means it's going to react more with my nitrogen. So my nitrogen is going to go down. And then opposite side same, my NH3 ammonia is going to go up. That also means that we would have more heat. But what side now is going to be favored? Well, we are going to have more of those products being produced. So products are going to be favored. And because that forward reaction is going to be happening more. If you want, take a minute, try the next one on your own. Removing LiOH. And as I look at this, how is everything else going to respond? Well, same side opposite. If I have less LiOH, that means I'm going to have more hydrogen, more heat. I'm going to have opposite side same. I'm going to be able to, with less lithium hydroxide, I'm going to be able to make less water. What's going to happen to lithium? Well, lithium's a solid, and so that concentration is not going to change. And so what side is going to be favored? What side is going to produce more? Or that would be our product side, because we have more of those up arrows. And so our product side is favored because that forward reaction is going to be occurring more. All right, last one here, our stress adding carbon. Well, if I'm adding carbon, how is that going to impact everything else? Well, carbon is a solid, so that is not going to have any impact on the rest of the system. And so there is going to be no change in equilibrium if we are changing that solid. So that's looking at what side is favored, what is going to be kind of more produced. We didn't talk about this last piece of how is that KEQ value going to be impacted. If we're changing concentration, your KEQ value is not going to change as a result of that changing concentration. Any changes, because that KEQ is based on the value of all of these gaseous or aqueous pieces of the system, that's going to kind of have a proportional change. And so your KEQ value is going to have no change when we have a concentration change with that. And so that is always going to be the case. If we change concentration, it's not going to impact our overall KEQ value. All right, on to our next stress, temperature. So if temperature increases, again, Le Chatelier's principle says we want to counteract that change. If temperature increases, we need to use up that heat, favoring the endothermic reaction. So the chemicals on the opposite side of heat will be produced more so. And decreasing the temperature, system's going to produce heat, favoring that exothermic. You can still use that same side opposite side same when you are looking at this. And when we're looking at this, the KEQ value actually does change for a temperature stress. So we'll discuss how we can determine that. All right, looking at changing temperature. So with these ones, they do get a little trickier because you could have heat on either side of your reaction. And so we then have to look at, well, what reaction is favored? And so it depends on those two things. So, and with these, I do like to just go through and separate out what are my two sides of my reaction, just so I can be comparing across that line. So this first one is a decrease in temperature. And so we could see heat as just heat or as a numerical value in joules or kilojoules. We treat it like any other species. And our KEQ will change. We will look at that in at the end. So if we're looking at this one, our stress decreasing the temperature. Well, if temperature is being decreased, then if we want to use that same side opposite side same, that means there's going to be on the same side opposite more hydrochloric acid produced. Opposite side of the stress is going to behave the same as the stress, so those are both going to be down. And so we can see that that forward reaction is going to be favored. And so we are going to get more, and again, reactants to products, more products, because that is going to favor the forward reaction. How does that make sense in terms of our heat? Well, if we have less heat, we want to produce heat. And so this is going to favor the exothermic reaction in order to produce heat. So favoring the side of the reaction that heat is on. Our next stress, increasing temperature. We have that temperature or heat energy in joules here. If we were to increase that temperature, Well, how do we undo an increase in temperature? We want to use up heat. How do we use up heat? Well, an endothermic reaction is going to use up heat. And so that is going to favor our reactants because that reverse reaction is going to be an endothermic reaction. We can still use that same side opposite side same. As you are looking at that, we have same side of heat, opposite, NH3 is going to go down. Opposite side is going to behave the same as the stress, so those are both going to go up. And we can see that we have more of those up arrows on the left, which means those reactants are being favored. And again, we saw the more up arrows over here, meaning that was favoring the products. These are all gaseous, so those can all be impacted. Looking at this one, heat now is on with our reactants, so decreasing the temperature. If temperature goes down, we need to try and counteract that by producing heat, which means this is going to favor an exothermic reaction to produce heat. Well, for this to be exothermic, it's going to favor that reverse reaction. And so the reactants are going to be favored, which is the reverse reaction in this case. We can also look at same side opposite. Heat is going down, which means the species on the same side are going to behave the opposite. The opposite side of heat are going to behave the same. Both of those are gas, so those are going to go down. What side has the most? We have more reactants being produced. So again, that also fits with our exothermic. Try the last one on your own if you want. Increasing temperature. Here's our heat. Well, if heat's going up, we want to use up the heat, which means that this is going to favor an endothermic reaction, meaning it's going to favor our reverse reaction, and it's going to favor the reactants. If we look at our same side opposite, heat is going up over here, so same side opposite, CO is going to go down. Opposite side same, our O2 is going to go up. Our carbon is solid, so it's not going to have a change. But the side with those most up arrows as a response to the heat is the reactant side. So changing temperature is the only time our KEQ value will change. So only time the KEQ will change. As we look at this, remember KEQ is concentration of products over concentration of reactants. So we can consider looking at our arrows. How are those arrows going to change? So use your arrows to predict the ratio of products to reactants. So to determining if our KEQ is going to get bigger or get smaller is our goal. You're not going to be able to predict the actual number. So if we look at this one, this was product favored. Well, KEQ is products over reactants. So if our products are going up, KEQ, we have product going up, our reactants are going down. Well, what's going to happen if our numerator gets bigger, our denominator gets smaller? Well, overall, our KEQ value then is going to go up or increase. And so really you're just comparing how are those numbers changing, those concentrations. Looking at this next one for that KEQ value, reactants are being favored. So again, more reactants concentration, you might be able to consider, okay, that means that this is going to get smaller. We can also look at this over here, kind of writing that out as KEQ products. Well, my product is going to go down in concentration, but my reactants are going up. And so how is that going to impact that value? as we have the number on the bottom going up, well, that's going to decrease our KEQ value, or so that's going to get smaller. If you want, try the next two on your own. Decreasing the temperature. For this one, looking at that KEQ value, products over reactants. Well, my products are both going down. My reactants are going up. And so how is that going to impact my KEQ? My KEQ value is going to overall decrease because that number on the bottom is getting larger. Looking at this last one, KEQ, my product is going down. My reactant was favored going up. And so that is also going to be a decrease. So temperature is the only time our KEQ is going to change. If it is a concentration change like before, it doesn't have an impact. And as we look at pressure change, that also will not change our KEQ value. So our last type of shift or stress is a change in pressure. Just as a reminder, when we're looking at this, a decrease in volume of gaseous systems causes an increase in the total pressure. So if we remember back to the ideal gas law, and when we're looking at these with that ideal gas law, we are looking at amount is not changing because we're not changing concentration with this. We are not looking at a change in temperature. We're only looking at a change in the pressure. R is a constant, so that's not changing. And so as we're looking at these, a decrease in volume, so if volume goes down and nothing on this side is changing, to counteract that, our pressure is going to go up. So a reminder that that pressure-volume relationship is inverse when that is the only stress. And we're not going to look at multiple stresses being applied at one time. And then same thing, if volume was to go up, pressure would be to go down with that. And so if we're looking at a Le Chatelier's principle, we do want to remember our pressure-volume relationship, because if we're looking at changing pressure, we could also be discussing a change in volume. Le Chatelier's principle predicts that the system's going to respond to reduce total pressure. So decreasing volume means an increase in pressure. So if we are decreasing volume, here we are looking at this case in the middle. This is kind of our start equilibrium. If we decrease the volume, so we can see here the volume is greater, now the volume is smaller. Well, decreasing volume means that pressure is going to increase. What is going to happen with Le Chatelier's principle? It predicts the system will respond to try and reduce that pressure. So if the pressure goes up, Le Chatelier's principle says that we want to minimize that pressure. And how can we do that as we look at our reaction? If we're looking at this reversible reaction here, we can see that we have our P2. We have 2 moles of that, and those are here. We have our P4, which is here. So if we are going to be looking to minimize pressure, as we look here, we went from having 3 of the P4s and 4 of the P2s to now having more of the P4. Well, when the pressure was increased, our system shifted to the right. So shifting to produce more of that P4. Well, why does it do that? Well, to reduce pressure, we want less moles. We only have 1 mole of P4 in our reaction. And so this is going to shift to whatever has 1 mole instead of whatever has 2 moles in order to minimize that pressure. And so that's what we want to consider. We are not thinking of same side, opposite side, same. We want to think about how many moles do we have. If I want to reduce pressure, I want whatever side has less moles of gas. If I am increasing pressure, I want the side with more moles of gas. So looking at this one, we're going to just choose a side, and as we are comparing those moles. And if pressure is increased, the system's going to shift to favor the side with less moles, trying to reduce the pressure. If pressure is decreased, the system's going to shift to favor the side with more moles, trying to increase that pressure. With these, again, KEQ value doesn't change, but with pressure, we need to only be considering our gaseous chemicals, and so now anything aqueous would not apply. All right, so let's look at this. Increasing pressure. Well, if it's a pressure change, we need to compare moles of gas. On the left side, I have 1 mole of H2 and I have 1 mole of CO2, so I have a total of 2 moles of gas on my reactant side. On the product side, I have 2 moles of gas. And so if there is an increase in pressure, how is my system going to shift? Well, it's not going to shift in either direction. What side is favored? Neither, because the same moles on each side with that. So it is possible to not have that shift if we have the same amount of gas or same moles of gas on each side. And again, we ignore heat in these. Looking at our next one, looking at my gaseous chemicals, if I'm reducing pressure, so pressure, I'm going to look at my moles of gas. I have 1 mole of nitrogen and 3 moles of hydrogen. So 4 moles on the left. On the right, I have 2 moles of NH3. So as we're looking at those, we've got reducing pressure. Well, the stress is to reduce pressure. To undo that, I need more moles of gas to counteract that. So the side with more moles is our reactant side. So the reactants are going to be favored. And we want to produce more gas in order to counteract that stress of reducing the pressure. Decreasing volume. So decreasing volume, well, we know that volume pressure relationship. If volume goes down, pressure is going to go up. So this is the same as a stress of pressure increasing. So let's compare our moles of gas. On the reactant side, I have 6 moles of CO2, 6 moles of H2O, so that's 12 moles of gas. On the product side, I have 1 mole of C6H12O6 and 6 moles of O2, so that is 7 moles of gas. So if the volume is decreased and the pressure increases, to try and decrease that pressure, we're going to want the side with less moles, and so that is going to favor producing our products. Again, our goal is to decrease the pressure. So the side with less moles is going to do that. Looking at this last one, reducing the pressure. And again, reducing pressure. Our goal is going to be to increase pressure. Let's look at our moles of gas. Well, that lithium is a solid, so we're not going to consider how many moles of that we have, but we have 2 moles of H2O on the reactant side. I've got aqueous lithium hydroxide. That is not a gas, so it won't behave, or it won't be impacted by that reduction of pressure. I have 1 mole of hydrogen, and so I've got 2 moles of gas on the reactants, 1 mole on the products. So to reduce if we're reducing pressure, we're going to want to increase pressure to get back to equilibrium. So the side with more moles is going to be favored, and this is going to favor our reactants. So reducing pressure, we want more moles to increase that pressure to get back to equilibrium with that. And then again, temperature is the only thing that has an impact on KEQ, so no change on KEQ for a change in pressure or a change in volume like that. All right, here is another little summary of all of those things. There's a worksheet posted, and please reach out to your teacher with any questions.